So the second part of the notes here for chapter 11 really deal with modern and the most sort of accurate model of the atom. It's sort of where we're at now. We did move from orbits, these kind of discrete energy levels that the Bohr model built, and that we were really talking about conceptually with those Lewis dot structures, but we're no longer talking about them. They're useful for building up a conceptual understanding, but modern sort of understanding in this wave mechanical model is talking about orbitals. And it doesn't seem that big a difference, but the key thing here is that the orbits are discrete levels, like steps, if you will, right? So electrons could be on these different stairs. Orbitals make things a little bit more gray, or in this case, a little more pink. And so really what they're talking about is that, well, we aren't that sure. We can sort of make those electrons jump for hydrogen and illustrate that they're at different locations or different places. But honestly, it's more of a gradient. And so it's more of a continuum as opposed to these discrete energy levels. And so really doesn't seem like a big deal, but that's the shift from orbits to orbitals. And so orbitals assume that the electron is a wave as opposed to a particle. And it describes the region in space as orbitals where the electrons are most likely to be found. They're kind of like probability maps, if you will. And so that's where the electron is most of the time. It's actually impossible to know the exact location of electrons. And so, if you notice the name Schrodinger there, it does involve quantum mechanics and understanding, how the electrons can and can't be there at any given time. And so Schrodinger uses a model to describe the probability of the electron that might or might not actually be around the nucleus of an atom. And so basically it's conceptualized like this, and it's sort of like this idea that in the darker center, there would be more likely a probability of finding the electron close to the nucleus of the atom. And so the electron spends time 90% somewhere within that sphere. And so even 10% of the time it's outside the sphere. So as much as this is more modern, it's actually allowing a little bit more wiggle room. I don't go into the quantum mechanics of it, but the crash course chemistry here does. He actually says people shy away from it, and I am one of those people. But he feels like he can delve into it and truly understand quantum mechanics. So give that a watch if you're curious or want to challenge the crash course Hank Green to see if he can make it make sense to you. It's yeah, it's an interesting one. So basically, we're going to sort of take it for granted that Schrodinger knows what he's talking about and really just start to understand a little bit more of these probabilities or these orbitals. So orbitals have different energy levels, so that N1 to 4 still holds, but they also have different shapes. And so we have these two different sort of notations. The different shapes are indicated by letters. So S is spherical. P's are two-lobed, so you can see it's kind of like a dumbbell sort of thing here. And in the spherical, there's just one sphere, but in the p orbital, you could actually have three different orientations. So you could have it on the x, the y, and the z axis, if you will. So each orbital can hold two electrons, and these two electrons are going to have opposite spins on them. That's coming up in the notes. So each one's going to hold two. So the sphericals can hold two. You could have an electron here, an electron here in these dumbbell shapes, right? Each one's going to hold two electrons. If we move up, just talking about, again, these shapes of orbitals, D is indicated for four-lobed, so it's kind of like a four-leaf clover, if you will, and they can exist on five different axes or five different planes. So 3 planes, right? 5 planes for these four-lobed structures that we call D, right? So this is P, this is D. And then it gets a little bit ridiculous here, and I feel like I should be able to twist up balloon animals for you here. F just says see below. There's actually 7 different planes for this one. And it is definitely, it's a six-lobed structure, so multi-lobed, if you will, and those are the F orbitals. So we've got these different shapes, and now we're going to put them back together with those different energy levels. And so let's just come back to this in the lab. There's a lot of ways of imagining this. This is in the lab. There's a poster up on the wall on the Silver King campus anyway. So that's one way of conceptualizing these in the different energy levels. So we'd have 1, 2, 3, 4, and on up energy levels, right? The N1, N2, N3. And so basically here, if we kind of talk through, it says here that each orbital can have 0, 1, or 2 electrons. And there is another sort of principle that governs these. The 2 electrons are actually spinning in opposite directions. And that's how it allows, apparently, 2 electrons to inhabit that orbital. And so that's the Pauli exclusion principle, that somehow they figured out that the electrons can actually inhabit the same orbital if they're spinning in opposite directions. So these electrons absorb energy and move to higher energy states, but the states are continuous as opposed to discrete. And so what I was talking about, the difference is it's like a ramp, these orbitals, as opposed to the orbits and the steps, right? This is the difference between orbits and the Bohr model, or that planetary, and the modern wave mechanical model. And so this is orbits, or sorry, orbitals, right? And so we've got still energy levels like I just laid out on the side over here, but it's not like stepping stones. It's more of like a ramp, if you will. So in these ones, if we were to kind of dissect this, S orbitals can hold 2 electrons. P orbitals, because there were 3 different planes, can hold a total of 6. D orbitals, because there were 5 planes, each holding 2 electrons, not planes, right, can hold a total of 10. F orbitals, there were 7 planes, again with each one holding 2 electrons. And so basically this is the way that we can conceptualize electrons filling the space around the nucleus. So there's many ways to conceptualize it. We could, like I said, if I was better and could build you balloon models, I could actually show you all this. You can take a look at this image that I said is a poster on labs, right? That's a way to conceptualize the way electrons fill the orbitals around. Or we can build that up for ourselves. And this is on the next page of notes, so you might want to just sort of watch and then flip back and forth. Basically, these orbitals are going to nest together. And we know that we have the energy levels. Oops. And we'd have 1, 2, 3, and 4 as our energy levels. And then we're also going to have the shapes. And so the shapes were S, P, D, and F. And so each of these shapes is going to have an energy level. Remember that I said that the S hold 2, the P's hold 6, the D's hold 10 electrons, and the F's hold 14. And so you can basically make a chart sort of filling this out. So the third energy level for the spherical, and each energy level would nest together. So that's the second energy level of the spherical shape is bigger than the first energy level of the spherical shape. And again, these ones all nest together. If I were to take a look at the p orbitals on the first energy level, they would be the smallest, right? And so I would have the first energy level could hold 6 electrons. The second energy level, still I'm keeping that p6 the same. The third energy level, still the same. Fourth energy level, still the same. The D energy levels, I'd have my first energy level of the D shape holding up to 10 electrons. The second holding up to 10 electrons. The third holding up to 10 electrons. And the fourth holding up to 10 electrons. This is a way to kind of build this out. Now, the way that these fill, if I just kind of get rid of all this stuff that allowed me to build it up, I'm left with just these balloon animal shapes, and I'm going to just switch my color here because what happens is that they fill in this arrangement. It's going to fill that first 1s2, and then it's going to come up and it's going to fill the first p orbitals, taking up to 8 electrons. Then it's going to fill that second, and this looks kind of crazy, and if you think I'm a bit wacky, that's okay right now. This is the order that they nest together, and so the order they nest together fits this sort of like yellow path that's all diagonal. And I didn't do the F's out here, which I sometimes make mistakes on. I think we deserve a better image of this. So let's flip the page, and maybe one of these is going to resonate a little bit better for you. In your formula pages, you actually have this sort of an arrangement. And in your formula pages, as I'm making this video, we actually have a bit of an error to correct. I forgot in here, there should say 4F14 in there. So hopefully you're watching this at a time where it's already corrected, but we've got that same problem in here. And so fix. And it should be fixed on your periodic table if you're taking this at a later date. So in this way, this is what I was trying to illustrate before. And when I look at this, it doesn't mean a whole lot to me, but you can build it up. You could just list them all out. And this is another great resource. I think maybe the best resource, and the one that kind of gave me sort of this like moment, is to take a look again at that periodic table, kind of where we left off in chapter 4 at looking at the periodic table. The periodic table has this sort of hidden structure within it, and this was figured out after the arrangement of the periodic table, and so it shows the filling of the electron orbitals as you work through. So you can see here how these lanthanide and actinides have to be kind of fit in the that order of filling. So let's try some of these, and I think that it's something that you kind of have to do to kind of get the hang of it. And basically you can use any old sort of approach that you like. So there are some exceptions. Copper as one of those ones. Remember, I illustrated that in the notes where, you know, it didn't seem to make sense with the Lewis dot structures. With the orbital arrangement, it actually shows how close the different orbitals can be, so that it actually has options. You know, so you could have it either lose 1 or 2 electrons. And so when we take a look here at this, you can see just how close some of these electron levels are. And so that's where you get these multiple valences. You're not going to be tested on the exceptions because they're a little bit weird and wacky, and chemistry seems to have a number of exceptions. But this electron arrangement gets us closer than the Bohr model did at understanding valence electrons and how the electrons are arranged for chemical reactivity and also the ions formed. So let's start with helium. Helium would be number 2 on the periodic table, which means that there are 2 electrons to place. And so if I start, I can just take a look at the periodic table where it is, and I would see that I'm still in the s orbital. And so the notation for this would just be 1s2. This 2 up here is where I'm illustrating how many electrons I have to place. So this is the number of electrons. Let's build it up, and let's do one that's obviously got more than 2 electrons. So carbon is number 6 on the periodic table. That means that I have 6 electrons to place. I'm always going to start with this 1s2. Then I'm going to move up to the 2s2. And now I've placed 4 electrons. The next one to fill would be 2p4. 2p2. I've now placed 6 electrons. So there's 2 plus 2 plus 2 is this 6 electrons. And so if I take a look at the formula pages here and where carbon is, carbon would be right here. And so I've got 1s2 2s2, 2p2, right? Those are 2 electrons here. Okay, let's do another one. So we'd have sulfur, and if I find sulfur on the periodic table, it's number 16, so that means there's 16 electrons to place. 1s2, 2s2, 2p6 would bring me up to 10. Need to keep going. 3s2. So again, if you want, you can be following along in this orbital filling, right? Or you can be looking at the periodic table, one or the other of those. How many? 12. And so I'd have 4 more to go. I need to move up to my 3p energy level, but I'm only placing those 4 electrons. And again, so 2 plus 2 plus 2 is 10, or 6 is 10, sorry, plus another 6 gives me the 16 electrons placed. And so all of this is the energy levels illustrated for the atomic structure of sulfur. Let's take a look at potassium. Potassium has 19 to place. So I'd start off the same as the others, 1s2, 2s2, 2p6, and I'm now at 10, right? If I have to keep going, I have 3s2, so I'm at 12, and then I'd have 3p6 and 4s1. If I add all these ones up, I was looking at this energy level filling chart, right? Or I can find potassium on the periodic table and kind of use that as my guide. So potassium would be here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 puts me at the location of potassium. So either you're using this as your guide or this image. And these are in your resources. There's no need to memorize them. Iron has a whopping 26, which you're going to see the futility of this. So 1s2, 2s2, 2p6, there's 10, 3s2, 3p6, 4s2, and then at that point I just have 3d6 left to go. So you can kind of just add up as you go, or you can take a look at the periodic table. You can take a look at where iron is on the periodic table. So number 26 on the periodic table would put me down in here. And so you can kind of use maybe a combination of these. One thing that I'll note is that these stars are the location of the noble gases. So we talked before about noble gases having a stable arrangement, having a full shell. And so over here you can see that the p orbitals are full for all of those noble gases. And so as you're using this, you can shortcut, and that's what the next part of the notes is about. So with many electrons, obviously this can become pretty cumbersome. We're going to learn core notation as a shortcut for doing this. So core notation really just abbreviates everything up to the closest preceding noble gas with the noble gas in square brackets. And so this gives me a place I can abbreviate in my line of filling at the star with a noble gas. So this would be helium. This would be neon, right? And then you could start listing your orbital arrangements from there. Let's try some of these. So here's an example of iron using full notation or core notation. So you can see that this first part is replaced by argon, and then this is just tacked on the end. Obviously, much simpler to do. Let's do just a few more here using full notation and then abbreviate that to core notation. So chlorine would have 16 electrons to place. Oops, I should flip my page. So I'd have, 17 electrons to place. So I'd have 17 electrons to place. Full notation would be 1s2, 2s2, 2p6, placing the 10. 3s2, I'm up to 12, and I'd need 5 more, so I'd have 3p5, right? That's the full notation of chlorine. Using core notation, I'd step it back to the closest noble gas, which would be right there, and I could replace all of that with neon in square brackets, just listing this at the end, 3s2 and 3p5. So this is the shorthand. This is core notation down here, where you abbreviate some of the nonsense with the closest preceding noble gas in square brackets. One more in full notation. So nickel, if I were to do that one, has 28 electrons to place. 1s2, 2s2, 2p6. That's 10 placed. 3s2, 3p6. Oh my goodness, losing the plot. 4s2 and 3d8. Pretty sure I've got 28 done there. I could take all of this. The closest preceding noble gas would be argon, and all of that is abbreviated into argon. It's always after the p orbitals that you can kind of shorten this up. And then I'd list everything else after the argon. So 4s2 and 3d8. Doing the last three here, they're definitely shorter. You can do them with full notation and then core notation, or you could just use core notation for these. So I'm going to throw the answers up. I find that this is one you just have to kind of do for yourself. Strontium. Sometimes taking a look at these ones and finding them on the periodic table is a faster way, or maybe you're looking at this and seeing where those stars are to abbreviate and adding the electrons together as a total. So again, I'll just throw the answers up for this one. It's sometimes nice, I tend to put like how many electrons am I trying to place here, because it's easy to kind of forget what you're trying to add it up to. And really use all the resources that you have. None of this is meant to be memorized. It's about using the information that you have on your formula sheets. And the last one, iodine, would have 53 electrons, and you can imagine full notation and how maddening that would be. And that should be our bit on full and core notation. The last little bit here are just some properties of the periodic table. We're going to come back to these as we talk about chapter 12 next. But basically, we could talk about how big the overall atoms are. And so as the electrons fill orbitals, it changes the atomic size. Basically, the more electrons you have to place, the bigger the radius of the atom is going to be. And here, when you have fewer valence electrons, it actually allows the atomic radius to grow in that there's not as much sort of holding in, if you will. And so I always remember this as a snowman. So you can see the stacked balls, right? They get bigger as you go down. And then if the snowman fell over, he'd look like that, right? So as you go down, they get bigger, and as you go left, they get bigger. And this is just sort of a trend on the periodic table. We'll talk about a few other trends as we go through the notes here. So ionization energy is also significant. This is how much energy it takes to rip an electron away. And again, if I go back to other models that we've used to sort of conceptualize, we know that these halogens really did not want to give up electrons. They would much rather get an electron. So they hold tight on their electrons. Even if we were to take a look at the snowman, right, they'd be up at the head of the snowman. They're holding on to those electrons tight. They're holding them in close. Over here, they have a very loose grip on their electrons, right? Loose electrons, and so, or the weakest hold on them. And so in these ones, I think this is the wrong page in your textbook, sorry, we've got this idea that they hold on tight over here. It's hard to rip them away. And over here, they're really happy to give them up. They're really, really reactive with those alkali metals and the blowing up in water that we talked about before. So that's just the last little bit of chapter 11. We'll come back and develop this further in our discussions of chapter 12.